The next lesson that we're going to cover in our unit on reasoning and logic is about reasoning in algebra and geometry. The objective is to connect the reasoning in algebra with geometry. So if you liked algebra, you're going to like this lesson because it'll be a review of some of the things that you already know from algebra, but we're going to be applying some of these concepts from geometry about reasoning and logic to what you already know from algebra. So let's look at some of the properties of equality that you learned in algebra. So the first thing we're going to do is just take any three real numbers. We're going to take three variables, A, B, and C, and they can represent any real numbers. So let's look at the properties from algebra that we can state about these three real numbers. The first one's the addition property, and it simply says that if A is equal to B, then I can add the same number to both sides and I will still have an equation. I can take A plus C, and that's going to equal B plus C. So I can add the C to both sides of my original equation, which was A equals B, and I still have an equality. That's all the addition property says. Subtraction property is very similar. If A equals B, then I can subtract the same number from both sides. A minus C is going to equal B minus C, and I will still have an equivalent statement. I will still have an equality. Multiplication property says if A equals B, then I can multiply both sides of the equation by the same number, and I will still have an equality. So A times C is equal to B times C. The division property, if A equals B, then I can divide both sides of the equation by the same number, and I will still have an equation. There's only one exception, is that whatever you divide by cannot be 0, because division by 0 is not defined. So we have to say if A equals B and C does not equal 0, then I can divide both sides by C. A over C is going to equal B over C. And you still have an equivalent statement. You have an equation. The reflexive property simply says that anything is equal to itself. So it just says A equals A for the reflexive property. One way that you might remember this is think about looking at your reflection in a mirror. You're equal to yourself. So reflection and reflexive are similar words. That might help you remember that reflexive property means that anything is equal to itself. Any real number A is equal to itself, A. Symmetric property says that if A equals B, then I can exchange those and say that B equals A. The transitive property says that if A equals B and B equals C, then A has to be equal to C. So if two things are equal to the same thing, then they have to be equal to each other. That's another way of saying that property. So A is equal to B and B is equal to C. They're both equal to B, so that means that A and C have to be equal to each other. Substitution property just says that if A equals B, then B can be substituted for A in any expression. So let's write that. B can be substituted for A in any expression. The last property of equality is the distributive property. So, and all that the distributive property indicates is that you are using multiplication to distribute a term, we'll call it A, to each term of a sum or difference within a parenthesis. So let's look at how to write this. I have some real number A, and then in parentheses beside it we're multiplying that A times B plus C, a sum. So in order to do this, we're going to distribute the multiplication over the addition. So we're going to multiply the A times the B, and then we're going to add the next multiplication of A times C. Distributive property using a difference is similar. We have real number A multiplied times a difference, B minus C. And we're still going to distribute this multiplication over the subtraction. So we have multiplying the A times the B minus the A times the C. Next we have properties of congruence. So properties of congruence apply to segments and angles in geometry. So the reflexive property still just means that anything's equal to itself. So if I have a segment AB, then it's congruent to itself. Segment AB is congruent to segment AB. If I have an angle A, then it's congruent to itself. So that's all that the reflexive property says for segments and angles. They're equal to themselves. Symmetric property for segments says if segment AB is congruent to segment CD, then I can switch those and say that segment CD is congruent to segment AB. The same property applies for angles. If angle A is congruent to angle B, then I can switch those and say that angle B is congruent to angle A. Let's go to the transitive property. The transitive property of congruence for segments says that if segment AB is congruent to segment CD and segment CD is congruent to segment EF, then segment AB has to be congruent to segment EF. Once again, if two things are congruent to the same thing, then they have to be congruent to each other. So AB and EF are both congruent to CD, so AB and EF have to be congruent to each other. Same thing is true for angles. We can also say if angle A is congruent to angle B and angle B is congruent to angle C, then angle A is going to be congruent to angle C. last couple of definitions that we have. The first one is a proof. A proof is a convincing argument that uses deductive reasoning. And we will be using proofs in the next lesson to prove that angles are congruent. But first we're going to be starting with, in this lesson, just reviewing algebra and applying the principles here to make it easier to get into that. A two-column proof lists each statement on the left, and then the reason that for making each statement is called the justification. And the justification is each step is on the right side. And we will look at an example of that. Each statement must follow logically from the step before it. So let's look at problem 1. Problem 1, we have a diagram, and it asks what is the value of x. So we need to apply some of the definitions that we learned in Unit 1 to be able to work this problem. The first thing you need to identify is what kind of angles are these angles that are pictured. The angles, they're adjacent angles because they share a common side, share a common vertex, and they don't share any common interior points. The exterior sides of these angles, see, that's ray DC and ray DE, form a straight line. So that means that those two angles are linear pairs, just by definition of a linear pair. So we can state the angle CDF and angle FDE are a linear pair. And the reason that I can say that is because of the definition of a linear pair. So once again, in parentheses, I'm putting the reason, the justification for each step that I take. So now what leads me to the next step? I have to make another statement based on the statement that I just made. I just said that they're a linear pair. So what do you know about a linear pair? Well, a linear pairs, according to the linear pair postulate, linear pairs are supplementary. And so they have to add to be 180. So we're going to say that the measure of angle CDF plus the measure of angle FDE is equal to 180. And the reason I can make that statement is because of the linear pair postulate that we learned in Unit 1. So now that I've made this statement, I can make some substitutions from the diagram. So in the diagram, the measure of angle CDF is x. So I'm going to substitute x for measure of angle CDF. And the measure of angle FDE in the diagram is 2x minus 15. So I'm going to substitute that into the equation. And the reason that my justification for doing that is the substitution property of equality. Now I just need to solve this equation. So I'm going to combine like terms. You got 3x minus 15 is equal to 180. And my justification for doing that is I'm simplifying. When you combine like terms, you could say combine like terms. So now I'm going to add 15 to both sides. So I'm going to get 3x equals 195. The reason I can do that, I can add 15 to both sides, is the addition property of equality. The last step I can take is to divide both sides by 3 to solve this equation. So if I divide both sides by 3, then x is equal to 65. And I can do that by the division property of equality. So now I have solved the equation, and I've found the value of x, and I have justified every step that I've taken with one of the properties of equalities that we've reviewed, or one of the definitions or postulates that we learned in Unit 1 for geometry. Let's go on to problem 2. In problem 2, it just wants you to use the properties of equality and congruence. What is the name of the property of equality or congruence that justifies going from the first statement to the second statement? So let's look at A. A says that 7x plus 3 is equal to 24, and then the next statement indicates 7x equals 21. So what did you do to get from the first statement to the second statement? To get from the first statement to the second statement, you had to subtract 3 from both sides. So since we had to subtract 3 from both sides to get from this statement to the second statement, that is the subtraction property of equality. The next statement says that the length of segment RS is equal to the length of segment ST, and the length of segment ST is equal to the length of segment TU. So the second statement, to get to this statement, the next statement says that RS is equal to TU. What property allows us to make that second statement? So if RS is equal to ST and ST is equal to TU, then we can apply the transitive property. So that's the transitive property of equality, because we're talking about lengths of segments, not the segments themselves. If that had had a segment bar over the top of those, we would have used the transitive property of congruence, because it would have had congruence signs and not equality signs. Note the difference there. This is inequality of two lengths of segments, so you use the transitive property of equality. In problem C, you start with 5x is equal to 10, and the next statement says 10 is equal to 5x. What property did you apply to get from the first statement to the second statement? All it did was switch sides. So this is the property that says if A is equal to B, then B is equal to A. That's the symmetric property of equality. Problem number 3, we're using properties of equality and congruence. In this problem, you're asked to write a 2-column proof. And you're given that the length of segment AC is equal to the length of segment BD. So the length of AC, there's AC, is equal to the length of BD. So you're supposed to prove that segment AB is equal to segment CD. So let's make a 2 columns. Let's make our 2 columns. We have statements in our left column, and we'll have reasons for making each statement in the right column. So typically, you always start with the information that's given to you. And we will number these so that they'll match. We'll have a statement, and then we'll have a matching reason for making that statement. So the first statement is what is the information that we're given. We're given that the length of segment AC is equal to the length of segment BD. And we can make that statement because it's given to us in the given information for the problem. Now what we're trying to prove is what our last statement should be when we have, justified each statement and gotten to the last statement. So let's see what we need to do to get to that conclusion to prove that. Second statement, just observing from the diagram, we can see if we could just kind of plan this out. If we could subtract the length of segment BC from each of those segments, then we should have what we need to get the length of AB equal to the length of segment CD. So let's make the statement that segment BC, the length of segment BC is equal to the length of segment BC. And we can state that because of the reflexive property of equality, because we're talking about lengths of segments. Third statement that we can make. Since we're talking about segments, we need to apply one of the postulates that we learned about segments out of Unit 1, which was the segment addition postulate. Segment addition postulate just says, for instance, for the length of segment AC is made up of segment AB plus segment BC. And that's just applying the segment addition postulate. Well, we can make the same statement about segment BD. We can say that the length of segment BD, because BD is made up of segment BC and segment CD. So we're just going to add those two together. Segment BC plus the length of segment CD. And that's also the segment addition postulate. Fifth statement, let's see what we can do with these two statements. If we take the first statement that was made, that AC is equal to BD, and if we substitute, we've said that AC is equal to AB plus BC, so we're going to substitute it into the first part of that statement. And then we'll take the second segment addition postulate that we made, and we're going to substitute that into the right side of that statement number 1. And we can make a new statement. We can say AB plus BC is equal to BC plus CD. And that's just the substitution. Property of equality. Last statement that we need to make. We can now make the statement that we need to prove. We needed to prove that AB was equal to CD. And we can do that if we subtract BC from both sides. So we can make the statement that we need to make. AB is equal to CD because we've subtracted, if you subtract BC from both sides. So that's the subtraction property of equality. So that's your first two column proof, is using the properties of equality and congruence together to prove that these two segments, the lengths of these two segments, are equal.